Homework 6, problem 5, find the electric displacement vector D and the electric field E everywhere for the following system where I have a dielectric of radius A that surrounds a line charge of linear charge density lambda. The dielectric ideally extends off to infinity in all directions. To solve this problem, we're going to use the equivalent of Gauss's law. The Maxwell's equation, Gauss's law, their differential form for the displacement is del dot displacement vectors equal to the free charge. We're going to take this expression and we are going to integrate it, and that turns it right into the integral form of Gauss's law. Integral over some surface d2 x n hat dot displacement vector d is going to be equal to the q free enclosed. Now the q free enclosed, well, first we actually, I guess, have to draw our Gaussian surface. So our Gaussian surface will be a cylinder that surrounds this line charge symmetrically. It will have a radius s and it will have a height L. Now by symmetry we are going to say, that the D vector only has a component in the s hat direction, and furthermore the normal vectors, our ends on the top and bottom, are plus z and n hat is minus z. So the n hat dot s hat is going to give 0, and so the only contribution comes from the edge where the n hat is in the s hat direction. So s hat dot s hat gives 1. And furthermore, since this will only depend on the distance and it won't depend on the azimuthal angle or the height, this will simply be the surface area of the side of the cylinder. And so when I write that down, that's going to be 2 pi SL, that's the surface area of the side of that cylinder, times this d sub s. This has to be equal to the charge enclosed. Well, the charge enclosed is simply this linear charge density times L, so it's lambda times L. This is a trivial thing to solve. This says d sub s is equal to lambda over 2 pi s, right? And so it says our displacement vector is going to be lambda over 2 pi s hat. And this is true everywhere. Right? That's just true everywhere. Now, the dielectric constant for this problem is given, is epsilon r. And to find E, we're going to use the expression that the electric field is epsilon naught, epsilon, that this expression D is epsilon naught, epsilon r times the electric field. And so, solving for the electric field, we have that the electric field is 1 over epsilon naught, epsilon r times this guy. Now, epsilon r is equal to something not 1, epsilon r is equal to something not 1 in this region, and is equal to 1 outside of that. And so here I have a piecewise function. And this is a fairly trivial thing to write down, and so we'll go ahead and do it. I like writing it like this: 2 pi epsilon naught s hat for s less than a, and lambda over 2 pi epsilon naught s hat for s greater than a. Because what it shows us is it's effectively having a smaller charge density, smaller by a factor of epsilon over r, when I'm inside the dielectric. And that's kind of a neat effect. That's the screening of this linear charge density. And that is the electric field everywhere. So that is the solution for problem 5.